Hello everyone, welcome to this video. So today we are going to work on some review problems from limit and continuity. So let's get started with the first example. The graph below is the function f of x and we have to find these. So here you can see that this graph has a kind of break at x equal to -1. So at x equal to -1, a lot of things are going on the graph. You can see there is a clear break at x equal to -1. The first part of the question here is we have to find the limit as x approaches to -1 from the right. Plus means from the right. So when x approaches to -1 from the right, from this side, as you can see, from the right, here is the function. It is increasing and it is approaching closer and closer to -1. Okay, it is getting closer and closer to -1. So the answer for this one is equal to -1. Meaning of that is the right hand limit is -1. Similarly, down here in part D, we are asked to find the left hand limit. Limit as x approaches to -1 from the left. Minus means from the left. From this side. If x approaches to -1, okay, if x approaches to -1 from the left, the function value is decreasing and approaching closer and closer to this value, this y value here, which is -3. That means this one is equal to -3. That means your left hand limit is -3 and right hand limit is -1. So these two limits are not equal. That means the limit of the function at -1, this one part B, limit as x approaches to -1 of the function, this limit does not exist. D and E does not exist because the left hand limit and right hand limit are not equal. For the limit to exist, the left hand limit and right hand limit must be equal. Here they are not equal. You can see they are not equal. That's why the limit does not exist. And here is part C. In this one, we are asked to find the value of the function at -1. So here is -1. If we go down here, there is a hole, there is no value. If we go here, there is a hole, there is no value. But if we go up here, here is a dot. That means for x equal to -1, this is the value of the function, which is 4. So f of -1 is equal to 4. So this is how we can look at the graph of the given function and find the limit. One key thing to note here is if the left hand limit and right hand limit are not equal, limit does not exist. If they were equal, then the limit of the function will be equal to that value. Okay, that's the first example. Let's move on to next example now. Here is the next example. So in this example, we are asked to evaluate the limit numerically. When you're asked to find the limit numerically, meaning of that is we have to make the table and find the limit. So we have to find the limit numerically as x approaches to 0. So if we think of the number line, when x approaches to 0, that means we are talking about x approaching 0 from the left and also from the right. We have to approach 0 from both sides. So you can start at some value, say for example, -0.20, and then go closer and closer to 0 from the left. And similarly from the right, you can start at 0.20 and then you can go closer and closer to 0. That is from the right. This one is from the left. This one is from the right. Okay, let's make a table. So we use different x values for the left-hand limit. -0.20, similarly -0.15, you can say you're going closer and closer to 0. So -0.10 and then -0.05, and then you can also do -0.01, which is very close to 0. This is from the left. And once we have these values set up, what we do is we'll find the value of sine 6x over x, because our function here is sine 6x over x. So now what we have to do is we have to plug in the value of x as these different values, okay, into this function. And because we are talking about the trig function here, make sure our calculator is in radian mode when we evaluate this using calculator. So let me complete the table first like this. Okay. So if we plug in negative 0.20 into this function, the value of the function will be 4.66020. Now we'll plug in next value, negative 0.15. If you plug in negative 0.15 in your calculator and simplify, you will get 5.22218. So clearly you can see that the values of this function are increasing here. Let's plug in negative 0.10. So if we plug in negative 0.10, we get 5.64642. Again, the values are increasing, but you can see from 4.6 it went to 5.2. Now it's 5.6. So now it is increasing within 5. Now let's plug in this one. So if you plug in that, you'll get 5.91040. So now it has increased to 5.9, from 5.2 to 5.6 here, and here 5.9. Now let's plug in this next value, negative 0.01 for x, into this function and simplify using calculator. So we get 5.99640. So in the beginning, when you go from negative 0.20 to negative 0.15, you can see from 4.6, it jumped up to 5.2. But after that, it is increasing very slowly, and it happens to get close to 5.9, then 5.996. So clearly you can see that these values are trending closer and closer to 6. So we can say the left-hand limit, so the limit as x approaches to 0 from the left of that function, sine 6x over x is equal to 6, okay, because we are getting closer and closer to 6. So that is the left-hand limit. Left-hand limit of the function is 6. So we got the left-hand limit. Now what we need to do is we have to follow the same procedure and find the right-hand limit. So when we go from 0.20 closer to 0, what happened to the value of the function? So let's do that now. Again, we take that x value, and the different x values are, this case, it is 0.20. We are starting from here, and we want to go towards 0. Then 0.15, then 0.10, then 0.05, and finally you go very close, that is 0.01. So we choose different values of x. Let me complete the table. So here we want to find the value of sine 6x over x. We are going to plug in the values in calculator. So for x, if we plug in 0.20 and simplify this one using calculator, we'll get 4.66020. Okay, 4.6. If we plug in 0.15, you can plug in and check. I get 5.22218. Same as in the previous one. It has jumped from 4.6 to 5.2. Now, if you plug in 0.10 and simplify, what I got here is 5.64642. It's increasing again, but it is within 5 point something. If we plug in 0.05, like in the previous one, I'm getting 5.91040. And finally, let me plug in 0.01. What I get is 5.99640. So the values are increasing and again getting closer and closer to 6. So we can say that the right-hand limit as x approaches to 0 from the right of that function 6x over x is a 6 again. So clearly from the left-hand limit is 6, and here from the right-hand limit is 6. So we know that if the left-hand limit and right-hand limit are equal, the limit exists, and that will be equal to this value. So we can write, hence the limit as x approaches to 0 of sine 6x over x is equal to 6. So in this example, we are able to find the limit of this function numerically. So whenever you are asked to find the limit numerically, that means you have to make the table and you have to find the limit from the left and also from the right. And if they are equal, that will be equal to the limit of the function at the given point. So that is example 2. Now let's move on to next example. So here we have 2 questions. The first, we have to evaluate the limit. The first one is limit as x approaches to 6 of x cubed minus 216 over x minus 6. And here is the b. So let's first work on a. So let me divide the page here to 2 parts. Like that. Okay. Now here, if you try direct substitution, if you try to plug in 6, it will be 6 cubed, which is 216 minus 216, 0. And then 6 minus 6, that is also 0. So it will be 0 divided by 0. 0 divided by 0 is not possible. So what we have to do is, we have to factor the numerator. 216 is 6 cubed. So what we know is, we have a factoring formula from college algebra. A cubed minus b cubed. The factoring formula for a cubed minus b cubed is a minus b, a squared plus ab plus b squared. So we are going to use this factoring formula. So what we can do is, first we can write it like limit as x approaches to 6, x cubed minus 6 cubed over x minus 6. So in place of a, we have x, and in place of b, we have a 6. So if you use that formula, it will be limit as x approaches to 6, a minus b, that is x minus 6, and then a squared will be x squared, then plus, in the formula we have plus ab, so if we multiply x and 6, that is 6x, then plus b squared is a 6 squared, which is 36. And then divided by, in the denominator, we have x minus 6. So now that x minus 6, which is in the numerator and also in the denominator, gets cancelled like that. So we get limit as x approaches to 6 of x squared plus 6x plus 36. So now this fraction, the limit of this fraction is changed to limit of a polynomial function. So when we calculate the limit of polynomial function, we can perform direct substitution. So let's substitute. If we substitute 6, this will be 6 squared. The next one will be 6 times 6. And the last one is 36. So 6 squared is 36. 6 times 6 is 36 plus 36. So this is 36 plus 36 plus 36 are 3 times 36, which is 108. So that is the limit for the first part. So in the first part, when we perform direct substitution, denominator was 0. So we try to use the factoring formula to remove this denominator, which get cancelled here. And then we perform direct substitution to get the limit. So that is one way of simplifying the limit when we can factor and cancel it. Now, if you look at part B, we have to calculate the limit as x approaches to 0 of this function. So you can see direct substitution does not work here because when x approaches to 0, denominator will be 0. So we cannot have 0 in the denominator. But what we can do is, because this is the limit involving radical function, we can multiply by the conjugate. So what I mean by that is this. Limit as x approaches to 0, square root of 2x plus 4 minus 2 divided by x. We multiply by the conjugate of this numerator. So in the numerator, we have square root of 2x plus 4 minus 2. So when you multiply, it will be square root of 2x plus 4 plus 2 divided by square root of 2x plus 4 plus 2. So here, literally, we are multiplying by 1. So the value of the limit does not change. But it will help us to simplify and get the correct answer. Limit as x approaches to 0. Now, if you look at the numerator, we have this quantity minus that, same quantity, but plus that. So it is like the a minus b times a plus b, which will be a squared minus b squared. So it will be like 2x plus 4 squared minus 2 squared. And in the denominator, when you multiply denominator with denominator, it is x times the square root of 2x plus 4 plus 2. Okay. Now in the numerator, we have limit as x approaches to 0. In this first one, square and square root cancel. So that will be 2x plus 4 minus 2 squared, that is a 4, divided by x times the square root of 2x plus 4 plus 2. Denominator as it is. Now in the numerator, you can see 4 and 4 get cancelled. And finally, what we get is limit as x approaches to 0. Now, if you look at it carefully, here is 2x divided by x. 2x divided by x is a 2 divided by the square root of 2x plus 4 plus 2. And this is equal to, now you can perform the direct substitution here. So in the numerator, you have a 2. And in the denominator, if you look carefully, if you plug in 0, 2 times x, 2 times 0, that is 0. 0 plus 4 is a 4, and the square root of 4 is a 2. So that is 2 inside this, 2 from the square root, and there is also a 2 outside, which is 2 over 4 or half. 2 over 4 or half. So in this example, in part B, what we did is we found the limit by using the rationalization technique. We rationalize the numerator, or we multiply by the conjugate, and we got the limit. So that is another technique of evaluating the limit. Now we'll move on to next example, maybe example 4 here. So this question is on continuity. Let f of x equal to 6x minus 5 if x is less than or equal to 9. And then f of x equal to negative 3x plus b if x is greater than 9. If f of x is a function which is continuous everywhere, we have to find the value or maybe values of b. How many values we get, we don't know. Okay, so this is a linear function. This will be continuous everywhere. And this one is also a linear function. It will be continuous everywhere. So the only place we need to check here is, because here 6x minus 5 is for x less than or equal to 9. So if here is 9, then for x less than or equal to 9, the function is 6x minus 5. This side, the function is 6x minus 5. And on the other side, for x greater than, on the other side, it is negative 3x plus 5. Now, for the function to be continuous, it must be equal at x equal to 9. So that is where we start. For f of x to be continuous everywhere, value of the function at 9 for this one will be 6 times 9 minus 5 is equal to, the value of this function at 9 will be negative 3 times 9 plus b. So 6 times 9 is 54 minus 5, 9 times 3 is 27 plus b. 54 minus 5 is a 49, negative 27 plus b. Now if you add 27 on both sides, 49 plus 27 equal to b. And 49 plus 27 is 76. That means the value of b is 76. So meaning of that is, this function will be continuous everywhere if this value of b is a 76. Okay, if the value of b is 76, the value of the function will be continuous everywhere. So if here is 76, and if we evaluate the value of the function at 9, the value that we obtain from here and also from here, they will be equal. And they will be both equal to 49. Okay, they will be both equal to 49. So that's how we can solve problem like this one. Okay, now let's work on example 5. Evaluate the limit as x approaches to infinity of this function and state an equation of horizontal asymptote to the graph of the function f of x equal to this function. So we have limit as x approaches to infinity of 4x cubed minus 9x squared minus 7x over 7 minus 9x minus 6x cubed. So because this is the rational function and the highest power of x in the denominator is 3, to find the limit at infinity, we divide each term by x cubed. So this will be equal to limit as x approaches to infinity. So if we divide this one, the first term by x cubed, that will be 4 minus, if we divide the second term by x cubed, it will be 9 over x. And then if we divide the third term, 7x by x cubed, it will be 7 over x squared. Then divided by, if we divide this one by x cubed, it will be 7 over x cubed. And then we have minus 9x. If we divide that by x cubed, it will be 9 over x squared. And this one, negative 6x cubed, if we divide that by x cubed, it will be 6. Now what we know is, when x approaches to infinity, this term, this one, and this one all goes to 0. So it will be 4 minus 0 divided by 0 minus 0 minus 6. Or if we simplify this, what we get is, in the numerator it will be 4, and in the denominator it is negative 6. 4 divided by negative 6, or negative 2 over 3. So that is the limit when x approaches to infinity of this function. When x goes to infinity, that is the limit. Now in the second part, we are asked to state the equation of the horizontal asymptote to the graph of that function. So here, what we have is when x approaches to infinity, we saw that the function approaches to negative 2 over 3. Okay, when x approaches to infinity, this function approaches to negative 2 over 3. So meaning of that is, the equation of horizontal asymptote is y equal to negative 2 over 3. So equation of horizontal asymptote is y equal to -2/3. Or if you simplify this a little bit, if you bring this 3 on the left hand side by multiplying on both sides by 3, that will be 3y. And then if we add 2 on both sides, plus 2 equal to 0. So you can leave it here as y equal to -2/3 or 3y plus 2 equal to 0. That is the equation of the horizontal asymptote. But make sure you note that to determine whether the value is the value for horizontal asymptote or not, we have to check this condition all the time. So here what we saw is when x approaches to infinity, the function approaches to -2/3. So this confirms that y equal to -2/3 is the equation of the horizontal asymptote. So we have to look for the confirming statement to give you the equation of the horizontal asymptote. That is example 5. Example 6, find the equation of all vertical asymptote to the graph of the function f of x equal to cosine x over x squared plus 3x. So here we are looking for the equations of vertical asymptote, and the function given here is f of x equal to cosine x over x squared plus 3x. This function can be rewritten as f of x equal to cosine x over x times x plus 3. So denominator can be factored to x times x plus 3. Now you can see here, when x approaches to 0 or x approaches to -3, in both cases, when x is 0 or x equal to -3, the denominator will be 0. The denominator goes to 0. When x approaches to 0 or x approaches to -3, the denominator approaches to 0. Now let's look at some limits here. So let's find the limit when x approaches to 0 and x approaches to -3. Now limit as x approaches to 0 of the function, that is cosine x over x times x plus 3. Now you can clearly see here, when x approaches to 0, cosine 0 is 1, which is a finite value. And then 0 plus 3, that is also a finite value. But the only thing that you will get in the denominator is this one, x, approaches to 0. So that will be very, very small, getting closer and closer to 0. So you are dividing a finite value by very small value. Meaning of that is your value will be very close to or approaches to infinity. So we say that this limit is infinity. Similarly, let's find the other limit when x approaches to -3. Limit as x approaches to -3 of cosine x over x times x plus 3. So here also, if we look at it carefully, we can see that in the denominator there is x plus 3. So that quantity will be approximately 0 when x approaches to -3. But these values, cosine -3 is a finite value, and this one is a -3, that's a finite value. So when you divide, that is also a finite value. When a finite value is divided by very small value here, which goes to 0, then the result will be either positive infinity or negative infinity, depending on the sign. Okay, here. So clearly what we have seen here is, this is what we can say for the first one. Here we see when x approaches to 0, f of x approaches to infinity. Okay, when x approaches to 0, f of x approaches to infinity. Meaning of that is when this condition is true, Okay, only when this condition is true, we say that x equal to 0 is the vertical asymptote. So this implies x equal to 0 is a vertical asymptote. So that is one answer. We got the first answer. Okay, we got the first answer, that is x equal to 0 is the vertical asymptote. That's the equation of the vertical asymptote. Similarly, if we look at the second condition that we have done here, you can see when x approaches to -3, okay, when x approaches to -3, the value of the function approaches to infinity. So again, when x approaches to finite value and the value of the function approaches to infinity, in that case, x equal to that finite value is the vertical asymptote. So the next answer for us is x equal to -3 is a vertical asymptote. So technically, we obtain two vertical asymptotes to the graph of this function f of x equal to cosine x over x squared plus 3x. So always remember, we must show this condition when x approaches to finite value, the value of the function approaches to infinity. So if that condition is true, then only we can say that the x equal to that particular finite value is the equation of the vertical asymptote. Okay, so that should be something you must show. That is something that you must show in order to tell that x equal to 0 and x equal to -3 are the vertical asymptotes. Sometimes people factor this one. They see that when x equal to 0 and x approaches to -3, the denominator will be 0, and they start writing that x equal to 0 and x equal to -3 are the vertical asymptote. They got the answer, but they're not verifying it. So you must verify and you must confirm that these two values are the vertical asymptotes. Okay, that is example 6. Now we'll move on to example 7, and this is the last example for this video. So here we are asked to use the intermediate value theorem to show whether or not this function has a root on this interval from -2 up to 1. So for that, let's begin with the function. F of x is equal to x to the 5 plus x to the 4 minus 1. And we're analyzing it on the interval -2 up to 1. Now, if you try to find the value of the function at -2, this will be equal to -2 to the 5 plus -2 to the 4 minus 1, which is equal to -17. So the value of the function at -2 is -17. So if you think of the number line, okay, if you think of the number line, here is -2, and then here is +1. Or you can also consider this as your x-axis if you want. And then your y-axis will be somewhere there, like that. That's your y-axis. So what we saw is when x equal to -2, the value of the function is -17, somewhere down here. Okay, -2 comma -17. Now let's try to find the value of the function at 1. So if you try to find the value of the function at 1, f of 1 is equal to 1 to the 5 if we plug in, then 1 to the 4 minus 1, which is equal to 1. So that means when x equal to 1, the value of the function is 1 up here. This one there. So that is 1 comma 1. So now you can see that when we talk about the 0 of the function, when we say 0 of the function, that is the value of x for which the function will be 0. So now if at -2, the graph is here, and at 1, the graph is there. Definitely to go from there to there, the graph will definitely cross the x-axis somewhere there. So 0 is between these two values, between -17 and -17 and 1. So what we can write is, so f of -2 is less than 0, which is less than f of 1. So meaning of that is this 0 is between -17, because -17 is here, 1 is here, so 0 is in between. That's what I'm saying. So this implies, so meaning of that is, we have f of 2, okay? We have f of 2 at 2, at -2, f of -2 at -2, f of 1 when x is at 1. Similarly, we get 0 for some value which is considered as c by the intermediate value theorem. So that value is considered as c by intermediate value theorem. So we can say that c, okay, there is a c in the interval from -2 up to 1. Okay, there is c in the interval from -2 up to 1 such that f of c is 0. That is, the value of the function at c is 0. That is the 0 of the function. So this is true by intermediate value theorem. Okay, that is true by intermediate value theorem. So we can say that there is a real 0 between these two values for that function. Hence, there is real 0 for the function on the interval from -2 up to 1. So this is how we can use the intermediate value theorem, okay, intermediate value theorem, to confirm whether there is a 0 for the given function on the given interval. So that is the last example for this video. Thank you so much for watching. I hope you find this helpful.